Good morning, friends. I feel immense pleasure to be here for my last lecture of this course, that is Engineering Thermodynamics. I am Dr. Dwivedi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I have started this course with my full zeal, and I have completed all the 5 modules. That is, the first module is about properties of the substances and first law of thermodynamics. Second module is about the second law of thermodynamics. Third module is about psychometry. Fourth module is about power cycles, and the fifth module is heat transfer and the gas compressors. I have done all these courses in my before all the lectures. I have completed 15 to 18 problem solving exercises. More than 40 problems I have solved already. Now I am in the process of the last about the discussion on the question bank. And today is the last topic, that is element of heat transfer and the compression. So in this we will start the first question, that is discuss about heat transfer. So what is the heat transfer? We have defined heat as the form of energy that can be transferred from one system to another as a result of the temperature difference. So to have the heat transfer, we need the from high temperature, and another should be the low temperature, and this temperature difference should be present. Then only heat transfer will take place. A thermodynamic analysis is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another equilibrium state. So, how much amount of heat is transferred, that we have already discussed in the previous classes. The science that deals with the determination of the rates of such energy transfer is the heat transfer. So, how much energy is transferred in watt means per unit second, per unit time is called the heat transfer. The transfer of energy as heat is always from the higher temperature medium to the lower temperature one. Heat transfer stops when the two mediums reaches the same temperature. So if one is having 100, another is 20, slowly the 100 will reduce to less and 20 will increase. And then when both are reaching to the same temperature, your heat transfer will diminish. Modes of heat transfer, we know that we have the conduction, convection and the radiation. We have 3 types of modes of the heat transfer. Now we will discuss about the next question. Explain about modes of heat transfer, and first mode is conduction. We have the 3 modes, we have the conduction, convection and the radiation. These are the 3 modes. I will be discussing especially for the conduction. Conduction is the transfer of energy from the more energetic particles of a substance to the adjacent less energetic one as a result of interaction between the particle. Conduction can take place in solid, liquid or gases. In gases and the liquid, conduction is due to the collision and diffusion of the molecules during their random motion. So this conduction is also taking place in the gas and the liquid also, and it is happening due to the collision of the molecules of the gases and the liquids, fluids. In solids, it is due to the combination of vibration of the molecules in a lattice and the energy transport by free electrons. A cold can drink in a warm room, for example, eventually warms up to the room temperature. If you take one bottle of the can from the fridge and you keep outside, after 1 hour or 2 hours, you will see the temperature is same. Initially, it was very cool, but after some time, here we have the liquid, we have the aluminum foil, but after that, it will be cooled. As a result of heat transfer from room to the drink through the aluminum can be by the conduction. So this rate of heat transfer is dependent upon few terms, that is the geometry of the medium, which type of it is made, what is the area? It's thickness, material of the medium, and the temperature. So geometry, it is called area. Thickness is L. Material of the medium, it is conductivity of the K, and the temperature difference is delta T. So these are the parameters which makes the conduction possible. Illustrate rate of heat conduction with equation. So this is the next question, number 3. So here we have two walls are here, one solid. The temperature of this thing is T1 and another side is T2. So it is the temperature distribution profile from T1 to T2, and heat will move from this end to this end in this direction. Area is A in the both side, and the thickness of this thing is delta X. So experiment has shown that the rate of heat transfer, that is Q dot, through the wall is doubled when the temperature difference, that is delta T, across the wall or the area A normal to the direction of the heat transfer is doubled, but is halves when the wall thickness L is doubled. So this wall thickness, this, if you are doubling, the rate transfer will be reduced. If you increase the area, it will increase. If you increase the temperature difference, it will increase. Thus, we conclude that the rate of heat conduction through a plane layer is proportional to the temperature difference across the layer and the heat transfer area, but is inversely proportional to the thickness of the layer T. Rate of heat conduction is directly proportional to the area, temperature difference, and the thickness. Here, Q dot is equal to Ka T1 minus T2 by delta X, or minus Ka delta T by delta X. So here T1 is the temperature of the first wall, T2 is the temperature of the second wall, delta X is the length of this material, K is the conductivity, and which measures the ability of the material to conduct the heat. It is continuous process here. If you see here that in the limiting case, if we make that delta X extend to 0, the equation we can write in the form of differential form, that is Q dot of conduction is equal to minus Ka dt by dx. Here dt by dx is the temperature gradient, which is the slope of the temperature curve on a Tx diagram, the rate of change of T with X at a location X. Area A is always normal to the surface. Minus sign ensures that heat transfer in the positive direction X is always positive quantity. So this area is, this is the width and this is the height, if it is entering from this side. Okay, so we will not take this L for this area, we will take W and H. Here, if it is the 1 meter, it is a 30 degrees centigrade to 20 degrees centigrade, it is the copper. So you can calculate that this heat is 401 watt per meter. So in this way, if you increase this 1 meter and area is different, then this value of the silicon is this much, this is okay, this much. So as per that, the Q will be different. And this is called the Fourier's law. This is the Fourier's law. Discuss the thermal conductivity. Thermal conductivity, it is denoted by K, is a measure of material's ability to conduct heat. For example, if the K is equal to 0.607 watt per meter degree centigrade for water, and K for iron is 80.2 watt per degree centigrade for the room temperature. So we can see that the iron has got more conductivity than the water. So heat transfer will take in iron, it will be higher, much higher than the, I think more than 150 times it is there, which indicates that iron conducts heat more than 100 times faster than the water. Thus we can say that water is a poor heat conductor relative to the iron, although water is an excellent medium to store thermal energy. So the storing capacity and this thing are inversely proportional. So we can see here that we can say that water is a poor heat conductor relative to the iron, although water is excellent medium to store energy. Thermal conductivity of a material can be defined as the rate of heat transfer through the unit thickness of the material per unit area of the temperature. The thermal conductivity of a material is a measure of the ability of the material to conduct heat. A high value for thermal conductivity indicates that the material is a good heat conductor. A low value indicates that the material is a poor heat conductor or insulator. Now I will go for the next question, that is question number 5. Illustrate the convection heat transfer with diagram. So we have done with the conduction. Now what is the convection? Convection is the mode of energy transfer between a solid surface and the adjacent liquid or the gas that is in motion, and it involves the combined effect of conduction and the fluid motion. So a conduction and the fluid motion is required for this. The faster the fluid motion, the greater the convection heat transfer. In the absence of any bulk fluid motion, the transfer between a solid surface and the adjacent fluid is by the pure conduction. The presence of bulk motion of the fluid enhances the heat transfer between the solid surface and the fluid, but it also complicates the determination of the heat transfer rate. So this you can see here, the heat transfer rate, hot block to the cold. If you see here, the temperature is falling and here the velocity is also increasing. So as you have the high velocity, that much the temperature will be low. So it is a temperature variation of air, and here it is air flow and how much heat is rejected or how much heat is transferred. It is shown in this diagram. Discuss about types of convection. So we have the two types, that is the forced convection and the natural convection. Forced convection is called the forced convection if the fluid is forced to flow over the surface by external means such as fan, pump or the wind. So if it is not natural and we are giving some additional force to make the flow of the air or the flow of the water or any medium which we are making by some machines, we are pressing it to move faster, then it is a forced convection. Natural convection is called the natural or the free convection if the fluid motion is caused by buoyancy force that are induced by the density difference due to the variation of temperature in the fluid. See this figure here. Here we have the forced convection. So in this, first we will see the natural convection. Here we have the hot egg. Here we have the hot egg here, and this hot egg will take lot of time to cool by the natural. Slowly it is happening. But if you want to cool the faster, then a small fan you can put it, and all this motion will be in this direction, and so this is called the forced convection, and this is called the natural or the free convection. So that is the difference between these two. Now I will discuss about explain Newton's law of cooling. Very important law which we are going to discuss. Heat transfer process that involve change of phase of a fluid are also considered to be a convection. Due to the fluid motion induced during the process, such as the rise of the vapor bubble during the boiling or fall of the liquid droplets during the condensation. Despite the complexity of convection, the rate of convection heat transfer is observed to be proportional to the temperature difference and is conveniently expressed by Newton's law of cooling. So this rate of such type of convection is described by the Newtons, and it is called the Newton's law of cooling. So this states that Q dot convection is equal to HAS Ts minus T infinity, where H is the convective heat transfer, that is in watt per meter square degree centigrade. AS is the surface area. Ts is the surface temperature, and T infinity is the temperature of the fluid sufficiently far away from the surface. So we have seen here the Newton's law of cooling, that Q convection is equal to HAS Ts minus T infinity, and all terms I have described. So the convection heat transfer coefficient. So convection heat transfer is equal to H. The convection heat transfer coefficient H is not a property of the fluid. It is an experimental determined parameter whose value depends on all the variables influencing convection, such as surface geometry, the nature of the fluid motion, the properties of the fluid, and the bulk fluid velocity. Typical value for H are given in this table. This you can see for free and the forced convection. For the free convection of the gases, it is 2 to 25. And for the free convection of the liquid, it is 10 to 1000. Forced convection of the gases, it is 25 to 250. It means more than 10 times. And for the forced convection of the liquid, it is 50 to 20,000. And for the boiling and the condensation, when the phase change is there, this value of H is very high, 2500 to 100,000 watt per meter square degree Kelvin. So for the condensation and the boiling, it is very high amount is taking place. Describe thermal radiation. So we have, as of now, we have done with conduction and the convection. We have the three modes of the heat transfer: conduction, convection, and the radiation. We have covered few questions of the conduction and we have covered for the convection. Now I am discussing about the thermal radiation. Thermodynamic radiation or radiation is the energy emitted by matter in the form of electromagnetic waves or photons as a result of the changes in the electronic configuration on the atoms or molecules. Unlike conduction and the convection, the transfer of heat by radiation does not require the presence of an intervening medium. In fact, heat transfer by radiation is fastest at the speed of light. It suffers no attenuation in a vacuum. This is how the energy of the sun reaches to the earth. In heat transfer studies, we are interested in thermal radiation, which is the form of radiation emitted by the bodies because of their temperature. It differs from the forms of electromagnetic radiation such as X-ray, gamma rays, microwaves, radio waves, and the television waves that are not related to the temperature. All bodies at a temperature above absolute zero will emit the thermal radiation. So above the absolute zero, everybody will emit the radiation. Radiation is a volumetric phenomena, and all solids, liquids, and gases emit, absorb, or transmit radiation to varying degrees. Radiation is usually considered to be a surface phenomena for solids that are opaque to thermal radiation such as metals, wood, and rock. Radiation emitted by the interior regions of such materials can never reach to the surface, and the radiation incidence on such body is usually absorbed within a few microns of the surface. Now, I will discuss the question number 10. State the Stephen-Boltzmann constant. So, you can see here that the maximum rate of radiation that can be emitted from a surface at a thermodynamic temperature Ts in Kelvin on the Rankine is given by the Stephen-Boltzmann's law as Q emitting is equal to sigma As Ts to the power 4, and this sigma is equal to 5.670108 watt per meter square K to power 4. The idealized surface that emits radiation at this maximum rate is called the black body, and the radiation emitted by the black body is called the black body radiation. So if this much amount of radiation is done, then that body is the black body, and the radiation is called the black body radiation. The radiation emitted by all real surface is less than the radiation emitted by the black body at the same temperature. So we have to add some constant value. So here we can see here that black body when epsilon is equal to 0, if the temperature is 400 Kelvin, it will be emitting the 1452 watt per meter square of the area. So this is the, by this equation we can find out this value. And if it is not the black body, we have to make it that Q dot emission of the radiation is equal to epsilon sigma as Ts to the power 4, where this epsilon, the value will be, is called the emissivity of the surface, and its value is ranging from 0 to 1. For the black body it is 1, and for the fully it is not black body, means it is not radiating at all, this will be 0. Demonstrate the absorptivity. Another important parameter is absorptivity. So another important radiation property of a surface is its absorptivity alpha, which is the fraction of the radiation energy incident on a surface that is absorbed by a surface. Like emissivity, its value is from 0 to 1. So how much percentage it is absorbing and how much it is reflecting. So a black body absorbs the entire radiation incidence on it, and this value, the black body at the present absorber is perfect absorber, where alpha is equal to 1, as it is a perfect emitter. In general, both emissivity and absorptivity of a surface depend on the temperature and the wavelength of the radiation. Next, I will discuss about the Kirchhoff's law. So this Kirchhoff's law of the radiation states that emissivity epsilon and the absorptivity alpha of the surface at a given temperature and the wavelengths are equal. So for a given temperature and the given wavelength, lambda, both are equal. In many practical applications, the surface temperature and the temperature of the source of incidence radiation are of the same order of magnitude, and the average absorptivity of a surface is taken to be equal to the average emissivity. The rate at which a surface absorbs radiation is determined. So here we can see that Q dot absorb is equal to alpha Q dot incidence. So here this you can see, okay, this side is absorbing. So here alpha into incidence, how much it is entering, and the reflecting how much, it is 1 minus alpha Q incidence. So out of one part is absorbed and another is reflected. So where Q dot incidence is the rate at which radiation is incidence on the surface, and alpha is the absorptivity of the surface. For opaque or non-transparent surface, the portion of the incidence radiation not absorbed by the surface is reflected back. So some part is reflected back as it is shown in the diagram. The difference between the rates of radiation emitted by the surface and the radiation absorbed is the net radiation heat transfer. If the rate of radiation absorbed is greater than the rate of radiation emission, the surface is said to be gaining energy by the radiation. Otherwise, the surface is said to be losing energy by the radiation. Since it depends on the properties of the surfaces, their orientation relative to each other, and the interaction of the medium between the surface with radiation is very, very important. Now the next question is rate of heat radiation. When a surface of emissivity and the surface area AS at a thermodynamic temperature Ts is completely enclosed by a much larger or the black surface of the thermodynamic temperature surrounding by the gas. So the question number 12 is, what is the rate of heat radiation? So when a surface of emissivity and the surface area AS at a thermodynamic temperature Ts is completely enclosed by a much larger or the black surface at a thermodynamic temperature, T surrounding separates by a gas such as air that does not intervene with radiation. The net rate of radiation heat transfer between these two surfaces is given by the figure here. So here Q dot radiation is epsilon sigma As Ts to the power 4 minus T to the power 4 surrounding in watt. The emissivity and the surface area of the surrounding surface do not have effect on the net radiation heat transfer. So in this you can see that here is the surrounding, and from here it is a AS, epsilon, AS and the TS. This heat is radiated from this body, and from here heat is entering here. So the net is the difference between the surrounding and this TS. So it is a Q dot radiation is equal to epsilon, the value is given here, area is given, and TS to the power 4 minus T to the power 4 surrounding. The emissivity and the surface area of the surrounding surface do not have any effect on the net radiation heat transfer. 13th question, discuss the radiation heat transfer. Radiation heat transfer to or from a surface surrounded by the gas such as air occurs parallel to the conduction or the convection if there is a bulk gas motion between the surface and the gas. Thus, the total heat transfer is determined by the aiding the contribution of both heat transfer mechanism. For simplicity and the convenience, this is often done by defining a combined heat transfer coefficient H, combined that includes the effect of both convection and the radiation. Then the total heat transfer rate to or from a surface by convection and the radiation is expressed as Q dot is equal to H combined AS TS minus T infinity. The combined heat transfer coefficient is essentially a convection heat transfer coefficient modified to include the effect of radiation. So I am here end of the course of engineering thermodynamics, and I really very much thank to the Principal, Institute of Aeronautical Engineering, Hyderabad, for giving me this opportunity. I have learned so much about making the videos. I give my full credit to the Principal of Institute of Aeronautical Engineering for giving me such a wonderful opportunity. Thank you very much. And these are the references which I have taken, that is Eunice Senegal, Bols, and NPTEL lecture from IIT Kanpur. Any questions you are welcome to ask. Thank you very much for the joining, and I have completed my lecture of engineering thermodynamics. Anywhere you have felt that I have done some mistake, it will be my honor so that if you can send me the feedback that there is some problem or some mistake, I will correct myself. Your feedbacks are very, very important. As this is my last lecture, I really appreciate your communication in this email, or you can comment on the YouTube channel also. I will be really very, very thankful for you all. Please do watch my channels, this topics. I also have the done for aircraft stability and control, and also I have done aircraft systems for BTech Aeronautical or Aerospace Engineering students. As of now, I have completed my 3 courses for more than 215 lectures I have done it. Thank you very much for the joining. Let's see for the next course very soon. Till then, goodbye. See you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.